Welcome to qnawire.
So in this problem, we're going to be investigating what the average force and pressure is from a bunch of stones making collision with a glass plate. Specifically, 500 of these collisions occur over a period of 30 seconds. And then here are a bunch of other parameters of the problem, like the angle of incidence, the velocity, the mass of the stones, etc. So an important distinction here is that these are assumed to be elastic collisions, and that is that there is no loss of energy when these collisions occur. So if you recall, this is exactly the same setup here as what we use to derive our molecular model for an ideal gas. And basically, the way we started this whole derivation when we were getting our ideal gas equations from the molecular model was that we looked at what the change in momentum would be in the x direction, delta p x, which in my drawing here, the x direction is going to be perpendicular to the plane of incidence. And what we determined is that's going to be minus 2 times the mass of our object times its component of velocity in the x direction. So we only look at the change of momentum in the x direction because that's the only component that's going to be affected in this collision. Again, exactly the same as for our derivations for the molecular model of a gas. So what we then did is we used the impulse momentum theorem to substitute for delta px over here with the average force times delta t equals minus 2 pix. And I should put subscripts on these. So I should put an I here on momentum and an I here on the average force because they're referring to a single molecule. So we then went on to use this to derive more equations, but for our uses, we can actually stop here. But the important thing to remember is this is just all exactly the same as the molecular model for an ideal gas. So if we take this equation here and we want to determine what the total force is, well, first we should isolate the force. So divide by delta t, right, minus 2m pix over delta t. And then we want to sum over all of the molecules because we want the total effect. So this is a sum over I. All right. So also, we should figure out what this component of velocity in the x direction is here. And we can do that with just a little bit of trigonometry. Actually, I've written my angle of incidence in the wrong place here. Oh, actually, no, I was good. Okay, so the x direction, or the x component, sorry, is going to be this guy right here, which is just going to be related to the magnitude of v by the cosine of the angle there, which is 45. So we can say that vix is just the cosine of 45 degrees. Or we'll be general for now and just say the cosine of theta. And that's going to be the same for, or we're assuming that to be the same for all molecules here. So there's no variation. All right, so what we should have is that the average force equal to the sum of all these average forces for the individual molecules, which is the sum of 2m cosine theta over delta t. So we can now see that there's no I indexes here in this sum anymore. So that means that the sum is just going to equal what's inside times how many elements we're summing over, which is going to be n, the number of molecules, or the number of collisions. So that will come out to be 2mn cosine theta over delta t. So at this point, we can just perform our calculation here. Which is going to come out to be 0.943 newtons if we plug all our values in there. Awesome. Now, let's determine what the average pressure would be from all these collisions. And this one's going to be nice and straightforward, because all we have to recall is that the average pressure will be defined as the average force over the area that all these collisions are happening on. So our area was just 0.6 meters squared up there, so 9.43 divided by 0.6. It's going to leave us with 1.7, 1.56 actually, newtons per meter squared. Cool. So there you have it. We have determined what the average force and pressure is from 500 elastic collisions occurring with this plane over a period of 30 seconds. And again, the important thing to remember for this whole problem was that we were just ripping off the exact same derivation for an ideal, or the molecular model of an ideal gas.